Now that you have opened your test bench here, now we can start writing our test bench. So we want to maximize this, and you'll see that the test bench that it created is just a standard empty module. So again, it just has a standard header, standard time scale, and the name. So to write a test bench, there's pretty much 3 simple steps. One is to make all of your inputs from the module you are trying to make. So let's do all of the inputs and outputs. We're going to copy these. And in the test bench, we're going to add them after this input output semicolon here. So we're not going to put them inside there. We're going to add them after. And instead of inputs, these are all going to be registers. So reg, So again, inputs become registers and outputs become wires. So that's step 1. Make your inputs registers and your output wires. But since we are assigning them after this parentheses and semicolon, you have to end each one of these with a semicolon. So semicolon, semicolon, and semicolon. So that's step 1. All your inputs become registers, all your outputs become wires. And now step 2 is to instantiate the module that you want to test. So to instantiate, all we have to do is go back to your module, copy the name. So just the name, Control C. So to instantiate it, you copy the name, you add UUT, so that just stands for unit under test. That is the name I'm giving it. You can change that name to be anything. But you do need the name of the module followed by the local variable name that you give it, followed by open parentheses, and then you do your inputs, so clock, reset, slot, comma, reset, comma, IN0, comma, IN1, comma, IN2, comma, IN3, followed by your outputs, comma, A, comma, B, comma, C, comma, D, E, comma, F, comma, G, comma, T, P, comma, AN. And you close parentheses and semicolon. So this is one way instantiating. This is the way I recommend for doing test benches, but for instantiating one module inside of another module, I will show you a different way in a later video. But for creating a test bench, this is the way to do it. So immediately after you have instantiated, I would go ahead and save it, just to make sure that there is no syntax error and so that it does recognize your instantiation. So to check that it recognizes your instantiation, you go back to your sources window here, and once you have saved it, once the asterisk is gone next to the name, then you can hit this drop box and you will see that the tutorial or the module we are trying to simulate is instantiated, which means has this little arrow that belongs underneath this test bench module. So this instantiation has worked. It's good to go. Next thing we have to do is initialize all of our registers. So let's do an initial begin, and go ahead and add n to go with it so don't forget. And in here we just want to initialize everything, so clock equals 0. I know we're going to make the clock oscillate, and I'll show you how to do that here in a minute, but for starters you want to you want to zero everything. Alright, so that zeroes everything. And here we can start adding some stimulus. So to simulate your module, what we're doing here is we're actually creating registers and wires, and we're inputting all these registers to the inputs of your module. So that's why we created all the inputs and made them registers. So this instantiation is actually plugging in these registers that we created into the inputs that they belong to. So we are plugging in inputs based on the values we give them, and here in the simulation we'll see what the outputs are doing. So to add delay in simulation, all you have to do is a pound, and then the value, the number after tells you how many nanoseconds, how many ticks. So here it says pound 100, its wait's 100 nanoseconds before it moves on to the next line. And for here we just want to do that. Kind of like that. Alright, so now we can change this input. Let's make that a 2. Add some more delay, so 100. And if we wanted to, or a correct simulation, a correct test bench for this module, you would want to change each one of these inputs to every single possibility that it can be. I'm not going to do that because of timeliness. It would take me forever to do all different possible combinations. But I am going to do a few to see what happens. So now I'll change this one to a 5 or something. These are just random numbers I'm coming up with. And then this last one I'll change it to a 9. Alright, so that's all the stimulus I'm going to add. And have begin and end. Alright, so hit save real quick, check for syntax issues. No, good to go. Alright, so the last thing you want to do is anytime you have a clock and you're trying to use the clock on the BASYS board, in simulation you have to simulate a clock that oscillates. So to simulate a clock that oscillates, all you have to do is in always begin, and you do pound 5 clock equals not clock. So that will just change whatever the status of clock is. So if it's a 0, it'll move it to 1, and then back to 0, and then back to 1, and so forth, so on. And it'll toggle it every 5 nanoseconds. Alright, and that should be it. So we'll go ahead and save this real quick. We can restore and highlight test bench. Now we can move down here to simulation. So let's run simulation, run behavioral simulation. And there we go. Here is our simulation. It shows you every single input, output, constant or variable that we have. It tells you their value and their type. And here we have all the signals. So we click on this one, it'll assume to fit. Here we see that our clock is oscillating. Here it goes from 0 to 2 to 5 to 9. And what we're seeing is that our outputs, our segments, are not being triggered to where they're supposed to. So our anodes and our segments, A through G and decimal, well, A through G decimal points actually working. But A through G is not being assigned the way it's supposed to. So to fix that, you would move back to your test bench. So close out the simulation, move back to your test bench and see where we went wrong. So in the test bench, we actually don't deal with the outputs other than where it lists them there, A through F, G. So it does say A, B, C, D, E, F, G, D, P, A, N. And here we have A, B, C, D, F, G, D, P, and A, N. Alright, so there is an issue in the simulation. If you find it, please let me know what the issue is. But for timeliness, I'm going to continue to programming the hardware. I know that this issue is in simulation only because I have already created this module before and I have programmed it onto the BASYS board and it will work. So I'm going to close up this test bench, move back to design source here, and start working on the programming for the hardware. So to program the hardware, first we want to go to tools, go to project settings, go to bitstream, select bin file, hit apply, and then OK. So when you program the BASYS3 board, there is a few different modes. I've mentioned it in my other tutorial, but here you see this blue jumper right here. It has QSPI mode, a JTAG mode, and a USB mode. So you can program it from JTAG straight into the BASYS or the FPGA, but whenever you turn it off, it will erase the memory. It'll erase the program. You won't have the program loaded anymore. So if you want it to load it to the memory over here, you have to set it to the QSPI mode, which is the top two jumpers. So top two jumpers, QSPI, middle two jumper, JTAG, bottom two, USB. So put that jumper up on the QSPI mode, and here I will show you how to program to the memory on the BASYS3 board. So the first thing we did was went to tools, went to project settings and changed that bit file. So again, highlight it, tools, project settings, bitstream, check bit file. And then we want to run synthesis. Okay. And as soon as this is done, when this window pops up, you want to open synthesize design. So as soon as it finishes and pops up that window, there it is. So open synthesize design, okay. This will open up the design. Alright, so now that it's open, you want to go up here to tools again, go to edit device properties, click on that, and here in general you want the enable bitstream compression to be true, so that's the first change. Then you go to configuration, you want the configuration rate to be 33, then you go to configuration modes, and you scroll down and you want to check, I didn't see it, hold on. there it is, the master SPI times 4. So check that little box and hit OK. And that will set some settings on your design. You can go ahead and close it. Make sure you hit OK and hit yes on the save, because you do want to save the changes that we just made. Hit OK. It wants you to write a XTC. Okay, so here we're going to create a new XTC. XTC is a Xilinx design constraint file. Call it 7seg XTC. That'll create the constraint file. Go ahead and close this again. Okay. Alright, so that constraint file, you should see it here in the constraint, called 7seg XTC, like we labeled it. For this constraint file, again, you want to scroll down here to properties, file properties. Let me compress this bottom part, expand this out. It's just so you can get more view on the properties here. But you want it to be only in synthesize and implementation. So that's good to go. You don't need it in simulation. It's not available. So the next thing you want to do is create the XTC file. So double click on that and you'll see that you have this blank page except for these 3 properties. These 3 properties are based on the changes that we made to the synthesize design. So we want to keep those 3 properties, but we also want to add all the components available on the BASYS3 board. So to create the XTC, we want to go to Google and look for BASYS3 Master XTC. Here you'll see a few links that will take you back to the Digilent site. The Master XTC is in the Digilent site, but a faster way to find it is this BASYS3 Resources XTC at Master link, and it'll be this first link, first and only link. Alright, so this will open up the Master XTC. You can highlight everything here, all 294 lines, and Control C, go back to your blank XTC file. So add a line and paste it. So here, if you look through what you just pasted, you'll see that every single component on your BASYS3 board is now listed as an appropriate set property and an appropriate location on here on the XTC. The hash marks are the comments, so all the lines are commented out, and it's up to you to uncomment the lines that you need. So to see which lines you need, you go back to your module, and in the XTC we are going to route all the inputs and outputs to their appropriate location on the board. So like we said, clock is going to go to the master clock, the oscillator, the 100 Hertz oscillator. So here you'll see that this is the clock signal. We just delete this £, and here is where we add the name. So CLK, we call it CLOCK. Here we also need this line and this line, so we'll uncomment those, change this to CLOCK. And there's one more that you have to change right here. CLOCK. Alright, so that sets clock. The next one we want to do is reset. So reset, we said, is going to go on a button. So if we scroll down, LEDs, 7 segment, buttons. So here we go. We uncomment this button line out. And instead of button C, we call it reset. Button C, reset. So button C does stand for the center button, so just keep that in mind that you are activating the center button to play the role of reset. So that takes clock and reset. Now we have to do IN0, IN1, IN2, and IN3. Those are 4 each, so we have to assign each one of their locations to a place. So we're going to use the 16 switches that are on the BASYS3 board. And we scroll up here, here's the switches. So I'm going to start with, actually I'm going to go ahead and uncomment everything. All the switches are going to get uncommented so that I can start writing in here, changing stuff. So I'm going to start with IN3. So IN3, position 3. And so if you wanted to know what location this is, you can see that it's V17, and you can look at your BASYS board and see that V17 is actually the farthest right one. So down here it says V17. So that's the farthest right one, so actually I'm going to make that one IN0. And I'm going to make that position 0. IN0, position 0. So now we'll see that's position 0. That's position 1. Position 1. Position 2. Position 2. Position 3. 3. And now we can move on to IN2. Or sorry, 1. That's position 0. IN1, position 0. IN1, position 1. IN1, position 1. IN1, position 2. One, position 2. 1, position 3. 1, position 3. And now we are at IN2, position 0. Position 0. Position 1. Position 1. Position 2. Position 2. Position 3. Position 3. Now IN3. IN3 position 0. Copy this part real quick. Oh. Position 0. Position 1. Position 1. Position 2. Position 2. And then position 3. Finally. Position 3. Alright, so that's all of our inputs. Look this over real quick, make sure there's no duplicates. Let's go together, let's go together. 1, 2, 2, 1, 3, 3, 2, 2. Alright, looks good. So that's all of our inputs. Next thing we gotta do is establish location for all of our outputs. So those are all the 7 segments. So when we scroll down, we see the 7 segment display is right here. And I'm going to assume segment 0 is A. Go ahead and uncomment all of this. So segment 0 is A. And it does have to be what we labeled them in our module here. So we're connecting the inputs and outputs themselves to location. So our output here is called C and or A, B, C, D, and E, F, and G. But if they were called segs like this one, then you would call it segs. Alright, G, and decimal points. Alright. So all of our segments are done. AN now needs to be done. So AN, they went ahead and labeled them already. So the AN position 0, AN position 1, AN position 2. So those are the same. So we can go ahead and save this. Our XTC is now done. And we can move back over to module. And now we can go ahead and generate a bit stream. So to generate a bit stream, you just want to scroll down here and double click on that. It's rerunning the synthesized design. But all of our settings should still be saved because they're at the top of this file. So now this will just take a few minutes, a few seconds maybe. Synthesize complete, implementation. So once this bit stream gets generated, the last thing we're going to do is open the hardware manager and program our memory device. So to program the memory device, we're going to have to add a memory device to the FPGA that we're working on. Okay, so let me see what's going on here. 15 through 70, 17 through 55. So here I forgot to add a box at the end. So that's important. You got to make sure you have all your curly brackets and your square brackets at the right place, or you will get error like we just did. Let me rerun implementation. Cancel, save this first. Now rerun synthesis. Alright, so that's done. We can run implementation now. Okay. So one thing I haven't mentioned about this window down here is that it does give you a lot of information. I don't know if you saw, I clicked on log. We're implementing, so I went to implementation, and now we can see everything that's going on with the implementation part. And yeah, if you can maximize this window, you can see a lot of good detailed information. It tells you exactly what step it's at, and when you get errors, this is a good place to look through to see what the error was and how to fix it. So in implementation, you see it says route design is actually routing the inputs and outputs to their locations on the BASYS3 board. So that's why we had to create the XCC before we did implementation, so that way it can map out all the appropriate inputs and outputs to their physical locations on the board. Alright, so implementation is done, so now generate bit stream. Writing bit stream. Again, this log will tell you everything that's going on. No errors, one small warning. Creating bitmap, writing .bit file. So if you see here, it says writing .bit file, writing .bin file completed successfully. Alright, so that's exactly what you want to see, and then you open up Hardware Manager. When you open up Hardware Manager, you also want to plug in your BASYS2 board to your USB and to your computer, and turn that bad boy on. Here, I've turned mine on. Now that it's on, I can go ahead and open target. If you have already opened it, it'll be here in your recent targets. If not, you go to open new target, hit next, connect to local server, next. It'll search for it and find it. You got to make sure you change the JTAC frequency to 30 megahertz. Again, that's the JTAC clock frequency, not the internal 100 megahertz. So the JTAC clock is always at 30 megahertz. Highlight this and hit next. Finish. And it'll connect to your device. So there you go. If you wanted to program the FPGA directly, you just right click here and program device. But again, that will be erased the first time you turn off your BASYS3 board. So to add a memory, you right click on the XC7A35T, right click on it, and scroll down here to add configuration memory device. Click on that. Here you want to search Spansion, S-P-A-N-S-I-O-N. And you want to select this S25FL32, FL032P-SPI, hit OK. And now it asks you if you want to program it now, so hit OK. And here is how we program it. If you did not get to this window, you could always, so now that we added the memory, it will show you in this hardware window that the memory is listed underneath the device. So you can right click on the memory and program configuration memory device. It gets you back to the same window, and then the program is the configuration file, so hit the dots here and look for your bin file. So again, most of the time I don't remember where my bin file has been saved, so it'll always save to the same location where your .v file. So your .v file always tells you the location of it right here. So for me, it's under 7-second tutorial, sources, new. So right click again, program configuration memory device. Now I can go to 7-second tutorial, sources. Alright, there it is. So if you saw, it was under 7-second tutorials, and then runs, and then there it is. If you click on it, it'll tell you when it's created. Mine was created like 2 minutes ago when I double clicked on that stuff, so that's the correct one. Hit OK, and notice that it says erase program and verify, so hit OK. And now it'll tell you that it is erasing. Now step 2, it is programming, and if you look at your BASYS board, you should see a little blinking light, a green light. Let me see, let me show you my BASYS board. Okay, so it's programming again. Sometimes it takes a little bit long, especially as your bit file gets bigger, as your module gets bigger, the more you start adding, the longer this will take. So this is another reason why you want to simulate and verify your module that way before you come to program it onto your board, because it will take longer. So now it says it's done. Now we can go ahead and look at our BASYS board. So here is my BASYS3 board. I can go ahead and turn it off, turn it back on. You see that the program has been loaded. Just to show you that it's not being programmed by the computer, I can unplug my USB port there, so it's gone. I can turn it off and on again, so you see that our program is loaded onto the board. And as we program it, these four switches represent the number for this digit. These 4 switches represent for second digit, and then 4 third digit, and last 4 last digit. So just to show you that, 4, 4, 4, and 4. So I turned on the first bit of every digit. So there you get a 1, 1, 1. If I wanted to give you 8s, then I would turn on the 4th bit. So those are 8s. And then 9s if you want to. But there you go. So now we have successfully created this module to program your 7-segment display. As you see, it is correctly running, and the center is the reset.